All right. So what did we do on Friday? Well, we started looking at identities. And people in the classroom will join us when they're able to. So we looked at verifying and proving. And in the red, there we have the steps for when we're verifying algebraically. So again, verifying, just like checking a solution, where we plug in a value that we're given into the equation and then simplify each side of the equation separately and then get to a point where the left side equals the right side, and then that's the verification. So that shows that the identity is true for that one value. And so that's what we did here. We had this one value of 30 degrees. We substituted it in over here in the blue part and then used exact values right away. So notice we're not using any of the identities at this point. So notice I didn't rewrite secant 30 as 1 over cos 30. I just kept it as secant 30. If on the side I needed to do some calculations to figure out what is secant 30, then I do that off to the side, but then I just substitute the value of secant 30 degrees, which was 2 over root 3. And then simplify, and we get left side equals right side. Ta-da! That was verifying. And we just do a lot of verifying over the next few days yet. And then we did the proof. So the proof here, we keep the thetas in, and again, we just simplify or modify the appearance of each side. Move this out of the way. Till we get to a point where, again, the left side equals the right side. And I think we finished this one off. And I think I asked you to do this one, but we didn't go over it. Is that correct? Anybody remembering this? Okay, so the first tip that I gave you when we are proving is that we can rewrite everything in terms of sine and cosine. And I said that always works, and it does. But I also said that's not always the fastest way to do things. So let me do this. Well, I guess I need to verify first. So I need to look at that 30-degree angle. Oh, I always forget to move this out of the way. Here we go. And I'll verify over on this side. So we have 1 minus tan 30 degrees equals and just to help me out here, I'm going to think of this special triangle. Ooh, pretend it's a triangle, and it's a right triangle, with this being my 30-degree angle. Again, you could look at this point on the unit circle, but for the special triangle, this would be a 1, a 2, and a root 3. And I'd remember that tangent is y over x. So this is going to be a 1 minus 1 over root 3. And on the right side, cotangent will be x over y. So I'll have root 3 is equal to cotangent 30 degrees. And then we get to pick which side of the equation we want to work on. Anybody have a favorite side here? Get some input early in the day. I'm going to pick Denise. Hey, Denise, which side would you like me to work on? The right side or the left side? Right side. All right. So on the right side, I'm going to rewrite this as two separate fractions. So since I have that denominator of root 3, I'm going to change this into root 3 over root 3 minus 1 over root 3. And then the left side will stay unchanged. And then fairly quickly I can see that those root 3's are going to cancel out on the right-hand side. So we'll just get 1 minus 1 over root 3. And I'm done my verifying. So the left side equals the right side. Good. Any questions with that one?
Is that the only answer we can get?
Well, it depends on if we worked the left side or the right side. You can't take anything across the equal signs. We can't multiply both sides of the equation by root 3, because if we were to do that, we're assuming that it's an equation, and we're not assuming that it's true. We want to verify that it's true. So we can only simplify the left side or the right side, or somehow manipulate it in some way. Is that good?
Yeah.
Okay. So if I had started with the left side of the equation instead, basically my work would have looked kind of like I was going up in this direction, where I'd start by getting the common denominator, the root 3 over root 3. I'd replace the 1 with that. And then I'd combine the numerators together to get the root 3 minus 1 all over the common denominator. So working kind of up from the bottom, that's what it would have looked like if I'd worked on the left-hand side instead. All right. So let's look at doing this proof. So I'm going to start with that tip that I suggested the other day, where I rewrite in terms of sine and cosine. So tangent of theta is sine theta over cos theta. And cotangent will be cos theta over sine theta. And there was a question there. Do I have to write left side equals right side at the end of all verifications? I would recommend it, just because in the past I wasn't emphasizing it, but on sample solutions that they've put out with diploma exams, they always put that at the end. And so they want to see something like that, so it's better to be clearer in the communication rather than just assume that I can just show the two sides are equal. It should be fine getting up to this point, as long as you show the left side equals the right side. But one thing they won't accept is, and I don't know why they won't accept it, but suppose instead of thinking of this with an equation all the way down, if we just did what's sometimes called a two-column proof, where I do that substitution on the left side, and then I do a line down here, and then I show that the right side is this. If that's all we do, and that's where we stop, what it looks like is that they wouldn't give us full marks, which I think is ridiculous, unless we actually got to the bottom here and then said, oh, this left side equals the right side. So I don't know why they're picky on that, but we want to be more careful rather than taking chances and hoping we get away with things. Okay, Zaid, thanks for the update there. I'm just gonna, I'll just leave that one looking like that, I guess. So continuing with the proof, and I'm going to use that strategy I had used the other day. Again, I could just take the reciprocal and multiply this denominator, but instead I'm going to multiply everything in the numerator by sine theta. And if I do that in the numerator, I have to do it in the denominator. So why did I pick this side? Well, this side I have fractions over fractions. And generally we don't like that. And so we have strategies for simplifying that. And so when I take this sine theta and I distribute it in on the right-hand side, I will get cos theta sine theta. And again, as I think I mentioned on Friday, remember the goal here is not simply to convince yourself that the two sides are equal, but to clearly communicate, I can spell, clearly communicate why the two sides are equal. So showing lots of small steps. So here these sine thetas can cancel out. Sine thetas there can cancel out. And I get to cos theta minus sine theta all over cos theta. So there I've simplified the right-hand side. I got rid of those fractions in the numerator and denominator. So I could keep working with the right-hand side, or I could actually do some modifying on the left-hand side. So why don't I do that, getting a common denominator here, multiplying this 1 by cos theta over cos theta. Which will give me cos theta minus sine theta all over that common denominator of cos theta. And now I have, again, left side equals right side. And we'll be fancy and say QED, D, not P, Q, E, D. Good enough. Okay, anybody have questions with that one? Yes, Prableen.
Um, do you have to show that you multiplied the 1 by cos theta over cos theta?
You mean show more than I wrote down?
Yeah.
Nope. Writing as much as I did. So what we want to do is we want to think about for anybody who's in our class, so basically at our level of math, what is a fairly clear and obvious step? So anybody kind of at our level, we would recognize that these two lines are equivalent. If I had jumped right from this line down to this line, it would be true what I've written up here is equal to this, but that's a pretty big step. And so thinking of not just what you're able to do, but what any Math 30-1 student could do, not necessarily in your class, but maybe it's a 30-2 student who's going to take 30-1 next semester, where math isn't necessarily their strongest thing. We'd say that this is too big a step to go from that top line down to this bottom line. Any other questions? No questions? All right. So let's go on to determining non-permissible values, which is something we didn't do last week. So when we're going to determine non-permissible values, so as we look at number 8, we have this identity. We're going to prove it in a moment. But first, we want to figure out what are non-permissible values for this identity. And there are two things we need to look at. We need to consider what are the restrictions on each trig function, and what makes the denominator 0. So here, let me do part A over on this side. So the cotangent of theta is equivalent to cos theta over sine theta. And since it's equal to this ratio, then that tells me I have a restriction. Since I can't divide by 0, the sine of theta can't equal 0. So it's kind of like solving an equation. And I think, oh, for what values of theta is sine theta equal to 0? So again, I think back to my graph. Sine theta starts at the center line, curves up, down, and back. And we're not told whether we're in degrees or radians, so I'm going to just assume that we're in radians. So there's a 0, there's a pi, there's a 2 pi. So I'm going to say I have a restriction that my variable theta can't equal multiples of pi. Because 0 pi is here, 1 pi is there, 2 pi is here, negative 1 pi would have been back over here. All right. Good morning, Ms. Godina. Thank you for being a hero for my class. And greetings, students. All right.
I have a quick question.
Yes. Who was that?
So,
Azifa.
me,
Okay.
Nazifa.
Thank you.
So you took sine to the denominator on the other side, but could we have not just done cosecant can't be equal to 0 and then solve that because that one's already in the denominator?
Well, I haven't actually finished this part of the question, so I also need to do that.
Okay.
So, for those of you in the classroom, I'm not sure when you joined us, but hopefully you've found the place in your notes. And right now we're determining non-permissible values for theta in the identity we're given. And when we're exploring non-permissible values, these two questions in the black box, those we need to think about. So far we're thinking about restrictions on each trig function. Cotangent, as we looked at last week, has some vertical asymptotes. And so those vertical asymptotes happen where the sine of theta is equal to 0. So where that denominator would be 0. And so I just looked at the graph of y equals sine theta and found the zeros of that. Those would be my restrictions for the cotangent function. All right. How are we doing in the classroom there? I see lots of people there. And I see the smartboard screen and Peter's fixing something. You have no sound. Is that the issue? Okay, let me type in the chat. Oh, now I'm speaking. Can you hear me now? Hello? Yes? No? No? Yes? Peter, talk to me. I can't hear you. Oh. You are speaking. Oh, you can hear. Mic isn't working. Okay. If you have that little headphone jack plugged into the side, unplug that and then hopefully the mic would work. It may not be plugged in, but it's just something to check. Nothing in the headphone jack. Okay. If you right-click on the speaker icon on the bottom right, you should be able to choose mic input. It's possible it just doesn't work on that computer, but you can always look there in the sound settings. I heard something. Yes, I can hear you now, Peter. Thank you. Good job troubleshooting. So we began this question of finding non-permissible values for theta. And what's in the black box there are the two questions we need to ask when we're looking for non-permissible values. So the first question we're asking is, what are the restrictions on each trig function? So I started with cotangent theta, and I thought of it in terms of sine and cosine because that made it a little bit easier for my head, because then I could see, oh, I have this sine theta in the denominator. I can't divide by 0, so I said sine theta can't equal 0. I looked at the graph of sine theta, got it here, found the zeros, and then wrote my restriction that theta can't equal multiples of pi. All right. In the classroom, can I get some sort of feedback? How are we doing with that?
Yeah, go to Peter. You can sit down with me.
I can hear talking, but I cannot understand if you're saying this is good or if you have questions.
Questions? Anybody? No, Mr. Wagner.
Okay, thank you, Ms. Godina. All right, next I need to look at that next trig function, which is cosecant theta, and I'm looking at where is this undefined. So this time I want to look at a different way we could do this. So I could have done this with the cotangent as well, but I could think of cosecant theta being r over y, and then I'm just going to think, oh, what makes this y 0? So I'll say y can't equal 0. So I think of my angle in standard position and think, where's my y value 0? I get a y value of 0 if I have a point on the positive x-axis or a point on the negative x-axis. We could pick any point, but most of the time we're going to pick something that would be on the unit circle, something like 1, 0, or -1, 0. Probably, and I'll get your question in a moment, but I think of this first angle is 0, this next angle there is pi, and then I'll be at 2 pi, and then 3 pi, and then 4 pi, and then I could go in the other direction as well. So again, I'm getting these same restrictions showing up from the cosecant theta function. Prableen, you have a question.
Why are we doing cosecant? I thought it was cot theta.
Because in my identity, I have a cotangent theta, but I also have a cosecant theta, and I have to consider each function that's in my identity, what restrictions does it have? That good? All right. So I also look at the cosine of theta, but I know the cosine of theta has a domain of all real numbers, which means it doesn't have any restrictions. So all the restrictions I get are going to be from this part here. So this is looking at that first question. What are the restrictions on each trig function? So this is also looking at that first question. So then I'm going to look at my second question. And the second question is, what makes the denominator 0? So here I'm looking at, well, cosecant theta it can't equal 0 because that would make my denominator over here equal to 0. So I need to consider this possibility. But let's think about cosecant for a moment. And let's think about it in a graphical way. We don't need to understand the graph of cosecant theta, but I'm going to show you anyhow because I think it'll help us understand this. So what I'm going to do to begin with is I'm going to do a sketch of the graph of y equals sine x, or sine theta. So the sine function curves like this. So that's y equals sine theta. If I was to look at the graph of y equals 1 over sine theta, I would do the reciprocal of this function. So remember, my maximum here is at 1. What's the reciprocal of 1? Also 1. So this point is on the graph of cosecant. Down here, my minimum was at -1, which means the reciprocal of -1, also -1, so that point is on the graph of 1 over sine theta, which is the graph of secant theta. Then, where is sine theta equal to 0? Well, 1 over sine theta would be undefined. So here, I'm going to have a vertical asymptote. Here, I'll also have a vertical asymptote. And then here down the y-axis, we have a vertical asymptote. And what we find, well, let's pick a point here. So a point here where y would be 1/2, the reciprocal would be 2, so my graph would be up there. And it'll be kind of similar on this side. So I actually get a graph that curves down. Oh, this is going to look really bad. Kind of looks like that. And here I'll get a graph, curves up, touches there, whoops, and then curves sort of like this. So this would be one period of the graph of y equals cosecant theta, where these graphs are touching at that point. Okay? Now I wanted you to see this because as you look at the graph of cosecant theta, where is that graph equal to 0? It doesn't get a y value of 0 anywhere. So this never happens. So cosecant theta can never equal 0. Nope, there we go. Which means I don't get any new restrictions by the fact that I have a cosecant theta in the denominator here. But that's considering this second question as I looked at my identity. So we finished part A, determining non-permissible values, and we found that what's in the box here in red, those are all the non-permissible values for this identity. Any questions? I'm not seeing questions. So now I'm going to give you a minute. Why don't you prove the identity? I'll give you a minute head start, and then I'll start writing up a proof. So again, I've replaced the left side with cos thetas and sine thetas. And I just want to emphasize something here. I mentioned it the other day, but just a reminder to be really careful when you have fractions over fractions, that if it's written like this, where here's my long line, I can tell that all of this was the numerator and all of this was the denominator. But if we were a little bit careless and we wrote it so it looked kind of like this, I don't know what's my numerator and what's my denominator. It's just confusing, especially if I had done something like maybe I drew this one really long. Then it looks like I have cos theta is my numerator, and then sine theta over 1 all over sine theta. So it looks like a cos theta over sine over 1, because this would cancel out, which actually works, but that's not what the question is saying. So if I saw this, I would take off a mark because this, what's written here, is not equivalent to what's up there. So I just need to make sure that my longest line is going to be this line here that's corresponding to this line up there, separating this numerator from that denominator. It's a detail, but it's an important detail. Prableen.
I was gonna ask if the line has to be equal in length.
It doesn't have to be equal in length as long as this one is your longest line, because that'll tell us this is numerator, this is denominator. What happens with these two, as long as they're shorter than this middle one here, then we're good. Okay, I'm going to multiply top by sine theta and the bottom by sine theta. And by showing that much work, we should be able to, at our level of math, see that these sine thetas cancel out, those sine thetas cancel out, and I just get cos theta. Now there is a danger of kind of doing lots of work in one line, that it becomes unclear what exactly was happening. So again, clarity is more important than efficiency. So make sure your communication is really clear as you work down the question. And again, we see the left side equals the right side. Anybody have a question with number 8? All right. Let's look down at number 9. And let me give you a head start to look at this question and figure out what will the non-permissible values be for this question, for this identity. So as you can see with what I'm doing on the right-hand side, I'm looking to see what makes cosine theta equal to 0. Again, I thought about the graph. This isn't the only way to do it, but this is just where my brain goes. And so here I'm getting this value at pi by 2, and here 3 pi by 2. So that's within one period. So I'll say that theta cannot equal pi by 2 plus k pi, because again, the distance in between these two is pi radians. And if I went another pi radians, I'd be reaching another 0 over here. So all of my zeros on the cosine function are pi radians apart. Questions?
I have a question.
Yes.
You have 3 questions.
I cannot hear.
Okay. Okay, good. I don't know. Currently, where did your 1 go for, like, originally it was cos theta equals 1 to r theta over 1 plus secant theta, so why did you get rid of the equation?
You're talking about question number 9, right?
Yeah.
Okay, so
Yeah.
I have not rearranged anything. All I've done is I asked, oh, I guess I was on the page. I asked this question: what are the restrictions on each trig function? So as I look at this, I say cos theta has no restrictions. Its domain is all real numbers. Cos theta has no restrictions. Its domain is all real numbers. Secant theta has restrictions. So I'm just looking for the restrictions on the trig function that shows up. So I'm not looking at denominators being 0 at this point. I'm just looking at what are the restrictions on trig functions that show up in the identity. Does that make sense, Karina?
The next question. Peter, no question anymore so far.
Okay. So that was the first part. The second question that we ask is what makes the denominator 0? So the denominator can't equal 0, which means 1 plus secant theta can't equal 0. So now I'm looking at the denominator and I'm solving this equation. Secant theta can't equal -1. And again, I could switch this to cosines. So I'd say this is 1 over cos theta can't equal -1. If I do the reciprocal of each side, I get cos theta can't equal -1, because the reciprocal of -1 is still -1. So that's going to be this point here. So that's where I get a y value of -1. And that happens at pi. So I get an additional restriction this time that theta can't equal pi. But now to get to my next point here, where the cos function would be at a -1, I have to go 2 pi radians. I have to go a full period. So I'll put plus 2 pi times k. And for both of these, I'm going to say k is an integer. So I have this restriction here, and I have this restriction here, and probably a good idea up here, since it's kind of far away, say k is any integer. Schloop. So those are both restrictions on this identity. Questions there?
We have one.
Excellent. Is somebody talking?
Yes. The question is how you get the restrictions for second part when the 1 plus c theta not equal 0.
Okay, so let me just scroll up here again for a moment. First question, I only look at the trig functions that are in my identity. If my identity has only sines and cosines, there are no restrictions for that first part. If it has secant, cosecant, tangent, or cotangent, each of those functions have restrictions, and if we were to look at their graphs, they all have vertical asymptotes. So we're looking for the restrictions on those functions. That was question 1. The second question we ask is, what's in the denominator of my identity? And then I have to keep in mind, in this case, I have 1 plus secant theta. So this denominator can't equal 0. So that's what I did for this second question down here. I took that denominator, said it can't equal 0, and then I solved that inequality. Does that answer your question?
Yes.
Good, thank you. And I thought there was a hand, but maybe there's not another hand. Okay, so again, let me give you a head start on proving this identity. So doing part B of the question. So I expect that this is probably what most of you did. You rewrote the secant theta as 1 over cos theta. And then again, I'm using that strategy of multiplying everything in the numerator and denominator by what was in the denominator, this cos theta. So I'm looking at what's in this denominator. So I multiply by cos theta here and cos theta there. So here's my tip. That is asking the question, what's motivating me to multiply by cos theta? What's motivating me is this denominator here of cos theta. So I want to make sure that I'm going to distribute this into these brackets in the denominator. The numerator is just a casualty in the sense that if I'm going to multiply cos theta in the denominator, I have to do it in the numerator, so I'm not going to expand the numerator. I could expand it, but what I'm going to find later is that I'm going to end up factoring this out again. So because my goal was to get rid of this fraction with the cos theta in the denominator, here I will distribute. Because I just had to do it here in the numerator, I'm not going to distribute, I'm going to leave it in factored form. And then you'll see what happens as I continue. one additional thing I should say, pardon me, is you want to make sure that you put brackets here if the cos is going to be multiplied to everything. So again, pretty picky notation stuff. As I've written it like this, so suppose I put this line there, if I didn't have these red brackets, it would be okay given this notation. But if instead my line up here had been extended a little bit further, like up to there, and then I had the cos theta over cos theta like this, then I have to have these red brackets so that it looks like this cos theta, which is multiplied to the numerator, is not just multiplied to this cos theta, but it's also multiplied to the 1. So just some really picky, clear communication that we need to keep in mind as we're doing this. But continuing back with the question, I'm keeping my numerator in factored form. And my denominator, I will have So here's where I'm showing a little bit less work than I did in some previous questions. But again, I would say this is a reasonable step that anyone in our course should understand. If I do cos theta here times this 1 over cos theta, it will give me a 1. Okay, so I'd say this is an acceptable step. The step isn't too big. Also, another thing that I would expect that at our level of math everyone would recognize is that 1 plus cos theta and cos theta plus 1 are the same thing. In other words, addition is commutative. The order we write addition doesn't matter. So if I cancel all of this bracket here and this entire denominator at this step, that's okay. And we finished our proof. So here you can see why it was actually a good thing that I didn't distribute this cosine into the brackets, because I found this common factor of 1 plus cos theta between the numerator and denominator. Any questions?
Could you do the one with the exact values?
For verifying?
Yeah.
Yeah, so we weren't asked to do that for this question, but we could do it. So let's pick a different angle this time. Let's use pi by 4 to verify. Okay. Let me see. Cos 1 plus cos over 1 plus secant. Okay. So we will verify for theta equal pi by 4. So then we'll have cos pi by 4 equals 1 plus cos pi by 4 over 1 plus secant pi by 4. That was the identity rate. Yep. Okay, so then let me think unit circle this time. So if I think on the unit circle and I'm looking at this diagonal that goes up there, this point, so I had another line down here, had another line up there. The ordered pair here was root 2 over 2 and root 2 over 2. So for cos pi over 4, that'll be equal to root 2 over 2. And then secant. This is where actually the special triangles would have made it a little simpler, because secant pi by 4 would just be a root 2, but I'm going to use the unit circle again, so this will be a 2 over root 2 if I got it from the unit circle, just doing the reciprocal of this x coordinate. And then Here I have a root 2 in the denominator. There I have a 2 in the denominator. So I'm going to multiply everything on top by 2 root 2, because that would be the common denominator between these two, and everything on the bottom by 2 root 2. And both my numerator and denominator, I need to fix fractions that are there, so I'm going to distribute in both of them. So that'll give me a 2 root 2 plus, here the 2's will cancel out, and I'll get root 2 times root 2, which is a 2. And here I'll get a 2 root 2. And here the root 2's cancel out, so I just have a 2 times 2, which is a 4. So I look at my left side, I get a root 2 in the denominator, I should say numerator, a 2 in the numerator. So I'm going to look to see if I can pull out a common factor up here to clean things up a little bit. And I can factor a 2 out. Something's looking fishy to me here. Why is that? I don't know. I think it must be fine. Let's just see what happens. So we'll factor out a 2. So here I can get some 2's canceling out. This is a good one to go over because it's not simple. So now I look at the two sides and I say, oh, I don't know, how could they possibly equal each other? Well, I can see on the left side that my denominator is a rational number. It's just a 2. So I have that strategy for rationalizing denominators that we learned in grade 11, where I could multiply this by its conjugate. So we were going to talk about that in our next lesson, but it's great that we're looking at it here because that is kind of setting up the stage for multiplying by conjugates. So remember the conjugate radical, I keep the first term and the last term the same, but I use the opposite sign in between. So here I'm going to hesitate with expanding my numerator. Should I? Maybe I shouldn't hesitate. So the reason I'm hesitating is because I want to rationalize my denominator. And so there for sure I need to multiply things out. So let me just leave the numerator at I'm not even going to write it in yet. I'm just going to focus on the denominator. When I multiply the first terms together, root 2 times root 2 gives me 2. When I multiply the outside terms, I'll get well, maybe I'll show every step this time. In the future, we'll skip some steps. This will be a minus 2 root 2. The inside terms will give me a plus 2 root 2. And there you can see these two will cancel out. So that was the real value in multiplying by the conjugate. And then I'll have a minus 4. So my denominator will simplify to 2 minus 4 is a negative 2. So let's expand that numerator as well. Root 2 times root 2 is 2. 2 times negative root 2. And then the 1 times root 2. And then the 1 times negative 2. So in the numerator, I have the 2 up here, and negative 2 there, they will cancel out. So this and that are canceling each other out. These two are like terms that I can combine together, and that'll give me negative 2 plus 1 is a negative 1 root 2. Oh, now I'm so close. Negative over negative gives me positive, and so I'll get root 2 over 2. And my left side I just kept as it was all the way down. I wasn't intending to do that, but that's an excellent question. Who asked for that?
I have a question. Question, Mr. Wagner.
I am listening.
Why did you multiply 2 root 2 instead of 2 over 2?
Why did I multiply 2 root 2? Sorry, you cut out part way through there, Karina. Can you ask it once more?
Why did you multiply 2 root 2 to the whole thing instead of root 2 over 2?
Are you talking about this line here?
If you scroll up a little bit.
Yes. Oh, up here. So this is your question from this step right there?
Yeah.
Okay. So what I was doing is I was looking at, here I have denominator of 2, there I have a denominator of root 2. What's the common denominator? Well, it's the product of those two. So that's why I multiplied by the product of 2 times root 2 on the top and the bottom. Is that good?
First is always try to eliminate all denominators. This is what is the point. As soon as you don't have any denominators, just the terms, it's easy to do all the things. Is it okay? Fine. Thank you, Mr. Wagner.
You're welcome. For those of you who actually want to see a more efficient way, what we could have done, instead of multiplying it by this 2 root 2, I could have just multiplied it by 2, and then I'd remember that 2 is the same as root 2 times root 2. Right? So this would be multiplying numerator and denominator by the same thing. It would have saved me a little bit of work lower down. But that might be beyond where some of us are ready to go. So don't worry if you don't understand what I wrote in blue. If you do understand it, great. If you don't, pretend it never happened. It never happened. Any other questions before we move on? Not hearing questions? We go to the last page. So on this page, we are just solving equations once again. So I did refer to this on Friday, said you could go ahead and look at it, but if you didn't, that's perfectly fine. So we want to solve this algebraically over this domain. So we're including 0, including the 2 pi. Now I have a sine x, but I also have a cosecant x. If I have two different functions, unless I can factor one out as a common factor, I'm kind of stuck, or I can use an identity. So in this case, I can use the identity because I know a relationship between cosecant x and sine x. So I could rewrite this as 2 times 1 over sine x. Then to get rid of this sine x in the denominator, I'm going to multiply everything on both sides of the equation by sine x. So I'm going to multiply sine x on the right side, and I'm going to distribute it right away, so I end up with this 3 times the sine x as well. And then sine x here times sine x will give me sine squared x. So again, remember that notation with the 2 here, that just means sine x times sine x. So that'll give me 2 sine squared x is equal to 3 sine x plus 2. And then I'll collect everything to one side. And this is a good point for me to stop and give you some time to review solving equations. So this would be like a 7.2 question. So I'll give you some time on that one. Well, actually, let me just kind of set up this next one for you. Here I have a sine x and a cos x, and there's not really a super, well, how do I rewrite one in terms of the other? So one option that I could do here, and I'll just bring it over here, would be to divide both sides by cos x and say, oh, sine x over cos x is equal to 1. But earlier I said we should never do this, because if I divide by cos x, I'm assuming that cos x can't equal 0. This is a situation where it's actually okay, but how do we know that it's okay? So I'll talk about that in a little bit. An alternative would be for us to say that if you remember that identity which says
And,
tan x,
yeah, I see that. How to see you. Oh,
do you remember this identity? I can rearrange this identity so that I have tan x times cos x is equal to sine x. So I could use that identity here to say that tan x times cos x, replace the sine x, and that has to equal cos x. So I'll work through this one in both ways, but that gets you set up for number 11 as well. I'll give you a few minutes now to work on 10 and 11, solving them, and then I'll go over them together with you. Any questions with number 10? Pravleen,
How'd you know that sine x equals negative 1/2 equals, like, how'd you solve it? Go from, like, sine x equals negative 1/2 to x equals 7 pi over 6 and 11 pi over 6
well, how do you solve equations?
by solving them?
By solving them. Do you use a unit circle or special triangles or graphing or inverse functions? What do you do?
I don't know. It depends on the question.
For this question, what did you do?
I didn't get there yet.
Oh. So what would you probably have done?
Probably negative sine inverse.
Okay. So if I did, so what I'm going to do, I'm going to start by sketching my angles in standard position. So I know here I have a negative half, which means I have a negative y value, or with the cast rule, I know that I'll be in the third and the fourth quadrant. So I'm going to say, suppose I have some reference angle here, alpha. So we'll say that the inverse sine of 1/2, so notice I'm ignoring the negative, that's going to give me the size of this reference angle. And we could do it in degrees because that'll give us an exact value, or we can do it in radians, divide out the pi, convert to a fraction. If we do it in degrees, we'll get 30 degrees. If we did it in radians, we get a pi by 6. So this, a pi by 6, and this also a pi by 6. So then when I'm looking for my angle x, I'm going to start here, and I'll go pi radians plus pi by 6 more. So that's where this one comes from. I'm doing pi plus pi by 6. And then to find my next one, I'm going to go all the way around here up to there, 2 pi, but I went too far. So I'm going to go 2 pi, and then I'm going to come back, subtracting off that pi by 6 to get me to this point. So that's how I'm getting this one. I'm going to do 2 pi minus pi by 6. Is that good, Prableen? Good. In the classroom, was there a question?
Yes, we have a question from here. How do you write the general term for this problem?
For the solutions? The general term would be just adding 2 pi k to each of our solutions that we have in the blue box over here. Is that good enough? Yeah, so this one doesn't have a more condensed and abbreviated version. Any other questions?
Yes, we have another one.
Okay.
If there were a more condensed answer, how would you find that out again?
Well, for more condensed, what we're looking for is, well, suppose we had something different. Suppose I had a solution here in the first quadrant where the reference angle is pi by 6, and then here in the second quadrant where the reference angle was pi by 6. So then I could just take my first answer and add a multiple of pi to it to get to this one over here. Similarly, I could get this answer, add pi to it to get that one over there. So that's one place that it sometimes shows up. Let me look at 2 other possibilities with you. So another possibility would be if we had 45-degree reference angles or pi by 4s, where suppose each of these reference angles was pi by 4. And what if we had the same thing here, where each reference angle was pi by 4? In this case, what we'll see is this angle here is actually going to be 90 degrees. And then this angle there, also 90 degrees, also 90 degrees, also 90 degrees. So in this situation, we would just say we have a solution of pi by 4 plus k pi by 2. Because if I add 1 pi by 2, it takes me here. A second pi by 2 takes me there. A third pi by 2 takes me here. A fourth pi by 2 takes me there. Okay, so that's another situation that we could end up seeing. One that showed up in the homework, which was kind of similar to this first one, but a little bit different. So this is not exactly the same, but the relationship is going to be the same idea. Suppose I had a solution that was up here on the positive x-axis. Then, let me pick a new color. This size of this angle here is a pi by 2 plus a pi by 6, which actually turns out to be a 2 pi by 3. And here, this distance in here, if this is a pi by 6, this is a pi by 3 on this side. This is also a pi by 3 on this side. So this whole angle here is a 2 pi by 3. And then we would find this one up there is another 2 pi by 3. So from section 7.2, the question wasn't exactly like this, but there was a solution that had where you're adding multiples of 2 pi by 3. And it was this kind of situation where we had the distance between each of our solutions was 2 pi by 3. And so in this case, the way we would write the general solution would be we'd write our first one, which would be pi by 2 plus 2 pi k, that's a 2, 2 pi k by 3. And that would have been the general solution if this was the case where we had a solution on the positive x-axis. So there are a couple places where we can find more condensed or efficient ways of writing a general solution. Again, you aren't required to be able to write them, just be able to recognize them if they're given to you in a multiple choice or numerical response question. Is that good?
Yes, so far, but we have another one.
Okay.
If you don't have an exact value, you get decimal answers.
Yep.
How do we know which?
Sorry, you got cut off in that last part. How do we know which solutions?
How do we know which solutions are found in our graph?
Okay. So, let me just get a new page here. Basically what it's going to come down to, if we think of a graph, suppose, oh well, yellow's okay. Suppose it was a cosine function that looked like this, and we were interested in these values here, whatever they were. What we want to do is we want to think of what are all the solutions in one period, and then what is the period. So suppose the period here was pi. So actually what I graphed in black there was y equals cosine of 2x. Suppose I had a 2x in there. Now my period is pi, so I'll take this solution, which I'll just call x1, and I'll add multiples of pi to it. And then I'll take this solution, x2, and I'll add multiples of pi to it. Suppose instead this was a 4, which would mean this would be a pi by 2, so then I would add multiples of k pi by 2. So I'd add multiples of the period to that. So I want to find all the solutions in one period and then add multiples of the period to it. Did that answer your question?
Not yet. I have like the solution, so I would add k pi over 2 to all four.
If the period was pi by 2, then yes, you would add k pi by 2 to all the solutions within that domain. Does that make sense?
Thank you. So far, so good.
Okay, there are only 4 minutes left. Less than 4. So I think probably I should stop there for today. This question I will finish going over in tomorrow's class, but I don't want to rush it for today. Here, just some tips at the bottom here. Start by simplifying the side of the identity that's more complex. So we've looked at that procedure and used that. And then if we rewrite both sides in terms of sine and cosine, that will also help sometimes. Okay, one other one that I'll just throw at you at this point will be look for an obvious identity. So sometimes there's an obvious identity that lets you simplify things quite quickly without changing everything to sine and cosine. And that'll probably become more clear as we do more of these proofs. All right. Any last minute questions?
Yeah, I'm here now. Will you post it on webcast, Mr. Wagner?
What was the question? Sorry.
Are you going to post these notes?
Yes, this is being recorded, so it'll be posted on EDSB.
I'm here. Are you coming back tomorrow or on Wednesday?
Wednesday.
Okay. Thank you.
You're welcome. Okay.
Bye, Mr. Wagner. I will send off.
Okay, sounds good. If anybody else has a question, feel free to stick around. Otherwise, you are free to go. Thank you for your attention and learning today.
Bye.
Bye. See you all masked up again on Wednesday.
Bye. Have a good day.
Thank you, you too.